Yes, hope all of us are doing fine. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. In this particular discussion, I'm going to look at the concept of the radius of gyration. Now, in our previous video, we had looked at the concept of the radius of gyration and considered it with respect to the moment of inertia, which we have done in some of our videos. Now, in this case, we are required to do an evaluation of the radius of gyration by showing that considering this specific form of a plane disk, which we are going to be seeing, we are going to be requiring to find the or to show that the radius of gyration of this specific disk is equivalent to 0.7071 r given as such. Now in this case, I've given three illustrations for the first one. Let's give it as A, B, and C. So this basically are going to be showing different dimensions of this specific, of course, disk, which is going to be shown as a cross-sectional area of this particular cylinder, and we're going to cut open this specific cylinder to show the different dimensions which we have given in terms of b, 2 pi r, and then this particular stretch of sigma r given as such, and they're going to provide for us a way of trying to find the radius of gyration, or show that the radius of gyration is indeed 0.7071 given as such. So we're going to look at this specific plane disk, which is going to be shown as that, and I've tried to look at it as of course a disk which is going to be made up of a series of concentric rings, and these concentric rings are going to consist of this specific cross-sectional area. So for this one, these concentric rings are going to consist of what we refer to as some sections of volume, and we're going to consider the thickness of these specific rings to be of 1 unit, which we can give in terms of delta r. So in this case, the whole aspect of delta r, the summation of this delta r are going to result in the whole radius, which is going to be given in terms of r, and therefore this radical thickness are going to be a part of the entire radius, which is going to be given in terms of r. Now, if the mass of this small ring can be given, or a section of the cylinder which is going to be given using this cross section ring is going to be given in terms of so let's consider the radius. So I can give this one in terms of so let's consider the radius of this small ring given in terms of delta r. So we can as well consider the mass of this specific section of the ring, which is going to be making up this cylinder, as sigma m given as such. And if we look at it that way, then therefore we can evaluate the moment of inertia of the small part of this specific total, given as the moment of inertia is given as of course the product of the radius, which is going to be given as such, and we're going to consider this specific section of the mass given as such. So this is going to be a general representation of the moment of inertia of this specific section, which particularly is shaded. Now in this case, we can as well give this specific moment of inertia as the summation of these small elements of course sigma I given as that one, which is going to be giving us the radius, or rather the this specific moment of inertia for this whole section given as such. So this one can further be given in terms of the square of r, and of course the summation of these mass elements given as such, and of course that's going to be giving us an of course an idea on how we can find the moment of inertia of this small, or the entire, of course, part of this specific of course cylinder which we have given as such. So we are going to consider the third case, whereby if we try to cut open this particular cylinder, we're going to consider the elementary thin cylinder which is going to be cut and rolled, and it's going to form a flat sheet as I've shown below, of the dimensions of b, 2 pi r, and the sigma r given as such. So we can find from geometry, you can find the volume of this specific cylinder as the product of course 2 pi r b, and then we're going to have the sigma r given as such, and of course that's going to form our of course volume. Now in this case, if we consider the aspect of mass as well, as we have looked at this specific section, mass is equivalent to the product of volume and density. So we are going to introduce a rho which is going to form our density. So therefore, for us to find the mass, it's the product of density times volume, which is going to be given as the product of the elements of volume and rho given as that one. And of course, that is going to be forming of course, this is specific aspect of mass. So in this case, we had said that we can evaluate the moment of inertia of this small element as the product of the square of the distance or the radius and of course that specific element of mass. And therefore we are going to find the product between this one and this one, which is going to be giving us this specific aspect of what we refer to as the moment of inertia. So in this case, we are going to take this specific aspect of this one and then multiply by this one, and that is going to give us the cube of that one, r, which is a product of this one. So we're going to have the product of this element of mass, and then we're going to have the square of radius. So the 2 is going to give us the element of radius cubed, and then we're going to have rho for that specific density, and then b. Basically, we're going to combine these specific elements which we have done basically on the upper part, and that is going to be forming. So I'll just see maintain this one as sigma r. So we're going to have this one as a representation of that small element as a moment of inertia of that specific evaluation. Now in this case, as this specific thickness gets thinner and thinner, we're going to replace the sigma r with dr, and thereby we're going to replace the sigma I with di. So in this case, that's going to assist us evaluate the moment of inertia. As this specific radius gets thinner and thinner, as we have said, it's going to be represented as the moment of inertia di, which is different from the sigma I given as such, which is the product of a density 2p, of course, pi r cubed, and then we shall have sigma r represented by dr given as such. And of course, for us to find the moment of inertia, we're going to do an integral of these two specific sections, which basically is going to be the di, or the integral of that one is equivalent to the integral of this from 0 to r for this specific radius over the values of 2 pi rho, and then we shall have b cube root over the cube of r dr given as such. And this, of course, if we do an evaluation, is going to be giving us the values of 2 pi b p. So this is going to be rho and not p. Rho, and then we shall have r to power 4, and then from 0 to 4. So we're going to do a substitution for that one and find the value of pi rho b r to power 4 all over 2, which is going to form our moment of inertia of this specific totality of these concentric rings, which are going to form the entire radius of r. Now we're going also to look at the concept of volume and mass of this particular disk, which we have considered. And of course, we're going to see that the volume of our disk is going to be, of course, given, this specific disk is going to be given by the product of the area of the, of course, the circle of our radius r, and then we're going to have that one multiplied by its specific depth. So in this specific case, we are going to just consider the concept of a volume from our previous discussion on geometry, whereby we're going to have it given us the area of that specific cross section, and then we're going to have that one with the length given as that one. So if we consider the aspect of mass as well as we have been doing, this is going to be given as the volume times the density, which we have given in terms of a rho. So therefore, this is going to imply that our volume in this case is going to be pi. So this is going to be pi r squared b times rho given as such. And of course, our mass in this case can be represented as a volume times density. Therefore, we are going to have that one given in terms of this specific representation. So in this case, it's going to be mass. So therefore, we shall have this one. I hope it's okay. So we're going to have a pi r squared rho and then times b. So this is going to be forming our mass in this particular case, which is going to be represented by the product of a volume times density times rho given as such one. And therefore, in trying to consider this specific case, we have just made, of course, this specific analysis for the moment of inertia given as such. Now, from our previous discussion, I've just given in our introduction to the radius of gyration, I had given a particular representation for the concept of the moment of inertia, which was given in terms of the moment of inertia is given as m the square of k, whereby we said k is going to form the radius of gyration. So if we were to consider this specific illustration which we have given, then therefore we can find the subject of k, which is a radius of gyration, that is our subject of interest, which basically from this formula is going to be given as the root of the moment of inertia all over the mass given as such. So in this case, we have evaluated the moment of inertia in this specific section, which is going to be given as that one. But we're going to consider the element of pi, rho, b, and of course, which is pi, r is the square of r, and b, and of course, rho in this specific case, and try to do a substitution for this moment of inertia. So in this case, we are going to see that for us in doing a substitution, this specific moment of inertia can be given in terms of mr squared all over 2. So in this case, this is going to be an evaluation from trying to give this element of m in this specific topic, so in this specific representation. So in this case, we are going to have pi, the square of r, so we are going to remain with the r squared, whereby the rest of the parts are going to be substituted by m, except this specific, of course, aspect of a half, which is given as such. So basically implying that this moment of inertia can be given using this specific fashion. So in this case, we are going to do a substitution of this moment of inertia in this particular equation for us to have, of course, a representation for the value of k, which is going to be given in terms of the root of mr squared from the previous version statement, which I've just given, all over 2 times 1 all over m given as that. So in this case, this is going to give us basically, if we try to give it in this fashion, this is going to give us the square over r all over 2. So for us to find the value of k, we're going to do a square of this one, which is going to be given as k is equivalent to r. So the root of square of r is going to be given as r all over the root of 2, giving us the value of k. So in this case, we are going to do an evaluation of this one. From evaluation, this is going to be given as the root of 2 is the root of 1 over 2. So this basically, if we look at it, is like the product of r times 1 over the root of 2. So this is going to be giving us the value of 0.701. So k is equivalent to 0.7071 r given as such. And that is going to be forming our representation of the radius of gyration shown by this specific evaluation. So I hope that that is comprehensive. So kindly check our description boxes for various links of other videos. Subscribe and engage us in the comment section, and also ring that notification bell for various updates of different topics in mathematics and sciences. So that is it for now, guys. Bye, God bless you. Catch us in our next video.